Okay, we've seen situations, and you've solved problems of situations of two balls running along parallel tracks. And when do they meet? When should this one be released so that it meets this one at this point? Moving in the same direction, when does this one pass this one? When do their velocities match? Those types of problems. Now, we can write a general model. We can just generalize this whole thing. There's only one system of equations that can apply to the whole thing. Now, there are parameters within those equations, you know, the coefficients of t squared and t and the constant terms and so forth, and we have to, you know, we can adjust those for whatever initial conditions we might have. We want a general model of two objects accelerating uniformly along the same axis. Okay, so let's let x1 be the position of the first object. Now, x1, of course, is a function of t, and I haven't written the t dependence there. And we're going to have an x2. It's going to be similar. The acceleration of the x1 object is going to be a1, which means that the second derivative of the position of the first object is going to be a1. Okay, so that's our starting point. We integrate that twice, and we find that x1 is of the form 1/2 a1t squared, where a1 is the acceleration, then plus b1t plus c1, where b1 and c1 are constants that are going to depend on the exact situation. Now, if we have specific information, we can find the values of b1 and c1 if we have enough information. And we can do the same for x2. Now, in the given situation, we said, okay, x1 at some time t1, and I say t1, 0, okay? Really, I probably should have said t1i, and I'm actually going to change that 0 to an I. Okay, t1 comma I is the time at which we know the position of this object. And also, let's just say that at t1i we know the velocity of this object. As it turns out, we don't have to even have the same time for both of these equations, but that's the way I have to write it for this given situation. Okay, well, if we know these, then we can easily evaluate b1 in terms of the t1i, and I've got t1, 0 there, t1, 0 there, but it's t1i, t1i. So we take our velocity function, which is, of course, the derivative of our position function. You can verify easily that this is your general antiderivative of a1, or the general derivative of your x1 function you got from integrating a1 twice with respect to t. We have this velocity function. If we know the velocity at this time, so this is the velocity at this time, then we just substitute this v of t1i is going to be a1 t1i plus b1, just substituting t1i for t in the velocity function. And that's got to equal this thing we call v sub 1i. Meaning that b is just going to be v1i minus a1 t1i. So we've evaluated our b1. How do we get c1? Well, you can work that out, but now that we know b1, the only thing we don't know up here is c1. So we can take our x, we can substitute t1i for t, and set this expression equal to x1i, and get c1 in terms of t1i and x1i. That is the typical thing that you do, and that I hope that we're used to doing. So it's maybe a little too much notation in that, but that kind of covers, in general, how we could do this. It's not completely general, because I should have used a different time here than I used here, but that's okay. That's easy to adjust for. If this time is different, then you just put that different time in here, you still get your b1. We do the same thing for the x2 function, and we get functions of the form x1 of t. I didn't put the t dependence in there, but x1 is 1/2 a1t squared plus b1t plus c1, whatever b1 and c1 turn out to be from our initial or whatever conditions we want to use. And x2 is of the same form but with subscripts 2 on the various parameters. So if we want to answer the question of when they meet, all we do is we set x1 equal to x2, this equal to this, okay? And I say equals 0. That doesn't mean that this equals 0. It means I didn't write out what you get when you move this over onto this side, but I'll go ahead and write it out right now. It's 1/2 a1 minus a2 t squared plus b1 minus b2 t plus c1 minus c2 equals 0. We just subtract all this from here and simplify it. It's very straightforward, you understand. If you don't understand why I wrote that down, just do it yourself. Ignore what I did and then see that you get the same thing. So right there is just a quadratic equation in standard form, in the form to which we can apply the quadratic formula. And we can find the time at which the position is the same. Having found that time, if we want to find the velocities, well, we can plug that into the velocity functions. I didn't write out, yeah, I did. Wrote out the velocity function here. Velocity function for the second object will be similar to this. So you just write these things out. That's how we would answer when the position is the same. If we want the velocity, we plug that time that we get by solving this equation into the velocity functions. Okay, so we get the two velocities if, when the two objects are at the same position, when they meet. The other thing is, maybe they don't meet. It's perfectly possible that this one starts out earlier than this one with a greater acceleration and a greater velocity. So this one never catches up, so they're never at the same point. In general, your graph of x1 of t and x2 of t, your graphs will be parabolas. So here's your t and here's your position, okay? Now in this case, there's at least one intersection point. And in any case where the two parabolas have different widths, if you like, different spreads, meaning that you have different values of the two accelerations. If they meet at one point, they'll generally meet at another, unless the point at which they meet is the vertex. Actually there are other cases. And you could have one parabola like this, another parabola like this, tangent to it at one point. And you could think about what that would tell you about the motion. You could have parabolas that do this. They never meet. One could be over here and one could be way over here. Of course, they would extend, but those two are never going to meet. They can meet at one point, they can meet at 2 points, they can never meet. And that all just depends on the discriminant, doesn't it? The discriminant, your b squared minus 4ac thing under the radical. If it's positive, then you're going to have 2 points of intersection. If it's negative, you're not going to have any points. You're going to have no points of intersection. If it's 0, you have 1 point of intersection. And of course, you need to know that about quadratic functions and what the quadratic formula tells you. Plain old late algebra 1, early algebra 2. How do we get when the velocities are equal? Well, we said V1 equal to V2. V1 and V2 are both linear equations. They're both derivatives of these, each is a derivative of the corresponding quadratic that's going to be linear, meaning you're going to have two straight lines, meaning that you'll have at most 1 point of intersection. Well, no. Meaning that you'll have either 1 point of intersection, and that's going to happen if the lines have different slopes. No points of intersection if the lines are parallel but don't meet, or an infinite number of points of intersection where the lines are, one line's right on top of the other. So you have infinitely many points of intersection. That means the two just move together. Or at least their velocities always match. Okay, it doesn't mean they're necessarily at the same position. If A1 is not equal to A2, the slopes are going to be different because the slopes are just A1 and A2. Another thing you got to be careful of when you do this is domains. Okay, If you start this one at this point, and this one at this point, and they're both moving in this direction, then if you start them at the same instant, then the domain begins at that instant. The domain is a set of t values that you can put into this and get a meaningful result. Okay? If you start this one later than this one, then the domain of this one is going to be different than the domain of this one. And we're just talking about the function that gives you the uniformly accelerated motion once they are released or given some initial velocity at some point. So you got to watch domains. You can easily, for example, this parabola is wider than this parabola. If these things are released at t equals 0 here, then none of this here on this side matters. And no part of this parabola that crosses the x-axis is going to matter. No part of this parabola that's to the left of t equals 0 is going to matter. So even though these two are probably going to meet somewhere to the left here, it doesn't mean they really met, does it? Because that point is outside the domain of at least one of the functions. I could say more about that, but I get into a lot of specific cases. You just got to be aware of domain.